Good. So this is then the real opening of the program in the sense that now really a module is starting, namely the neurocognitive methods in programming module. And as you might deduce from the title, these are actually two modules if you want. So one is neurocognitive methods and the other one is programming. And in neurocognitive methods, which will happen obviously in the next 2 weeks, we want to discuss the main two methods that are used in cognitive neuroscience to learn about the human brain, namely EEG/MEG and functional magnetic resonance imaging. And as you will see from the course outline, we try to cover kind of the physics part, the biology, and a little bit of the analysis part, but the focus is definitely more on the background information about the methods and hardly actually on data analysis, because for data analysis we have the statistical methods module, which will then start on October 14th, where we will focus in on frequentist statistics of fMRI data, which is a common thing in the winter term, and then multi-voxel pattern analysis in the summer term, so things that you might know as machine learning. Sorry, I have an issue with machine learning and MBPA. Anyway, good. Then let me first tell you a little bit about the neurocognitive methods of programming module this year. So the first part will, as I said, cover EEG and MEG. And this course is kind of, I guess, a course, like you've had many courses before. So there will be PowerPoint slides. There will not be many equations, and it's all about getting some background knowledge. And these PowerPoint slides and the courses are modeled and basically use the material in the Luck book, which is called An Introduction to the Event-Related Potential Techniques, which is more kind of an introduction to EEG in general, but with a focus on ERPs. And that's the EEG part, and my part is based on functional magnetic resonance imaging by Hüttel et al. So the fundamental idea of this neurocognitive methods part is that you read these books and memorize everything that's in them, and then you have learned something. Like all courses that I teach and all courses at a university and all courses in SCAN as well, these courses are meant to help you in your studies, right? So your studies are not these courses, but you are humans who would like to study social cognitive and affective neuroscience, or cognitive neuroscience in my world. So you would, if there would be no courses, what you would do is read these books and study them. Yeah, and if you are outside of university and maybe you get a degree in physics or so, and then at one point you would like to work in cognitive neuroscience, you would have to study cognitive neuroscience and you would read these books, or other resources, watch YouTube lectures and whatnot. So see these courses and also these kind of lectures that we're doing as help in your own studies. And I guess if you haven't read these books yet, has anyone looked at them? If you haven't read them yet, then these kind of lecture series that we're doing over the next 2 weeks will be your first exposure to the material. But of course, it means that you should look into these books to consolidate this knowledge, and then you have a solid knowledge base about the things that can be done with EEG and MEG and fMRI, and also things that cannot be done. From an intuitive, general knowledge kind of viewpoint. Yeah? If you won't know much about the data analysis, although there's also in these books, there's a little bit about the data analysis, you won't be able to really do any data analysis, but and you also will not really be able to do an experiment all on your own. But at least if somebody says we're going to the scanner, then you will know, okay, they need to the MR scanner, and we are now going to the MR scanner. Something like this. Or somebody says, these are the, shows you the electrodes, you know what the electrodes are in EEG, you know what an amplifier is. So that's kind of the aim here. And of course, you also know then if you read papers in other courses and they say we used 64 electrode EEG or something along these lines, you will have a little bit of a knowledge what that means. And it's important knowledge, so it's definitely important and required. Yeah, before I tell you about the programming, this is the outline. Essentially, it's always 2-hour sessions, meaning 2 lectures of 45 minutes. So I usually do 45 minutes, then we do a little break, then we do another 45 minutes. And yeah, so we start with EEG because that's much more natural and because it's closer to neural activity. And yeah, discuss then EEG, its physical foundations with a little of electricity, neural origins, so revising some of the neural stuff that you will know, and then discussing some basic phenomena in EEG, namely event-related potentials, which are good to know, so that if you are then in a seminar or something and somebody says P300, you will have a rough idea what P300 means. And in the end, some kind of other analysis types, so that after this course we can discuss the difference between induced and evoked power, for example. Then once we're done with EEG, we'll start with fMRI, and basically do follow the same kind of structure, some intuitive physics background, some signal generation, some biology, a little bit of data pre-processing, so that basically then when we start in October, mid-October, on the 14th, when we start with analyzing fMRI data, that you basically have everything that happens before you start analyzing data and now really modeling the data and doing data analysis, that you have kind of the background knowledge and have everything up to that point. Yeah, so that's the outline. The outline will feature many times, so don't worry if you have not memorized it yet. Then before we talk about the course requirements, let's talk about the programming business. So the programming business is a programming course that will happen in the summer term, so this module extends to both terms. And we will do kind of a seminar on programming in the summer term. One first important thing is the introduction to programming will be Python based, because I say so, and because it's so it used to be MATLAB based. Cognitive neuroscience used to be big in MATLAB used to be big in cognitive neuroscience and is still big in cognitive neuroscience. However, that has been so since the early 90s essentially, and of course it's now 30 years since the early 90s, and over the last 10 years definitely Python, or maybe 15 years better, Python has really developed as a good alternative, or as a good alternative for applied mathematical computing, and as a means to do data analysis, primarily outside of cognitive neuroimaging. And so basically, if you would leave cognitive neuroimaging to work in a startup in Friedrichshain, I don't know where the startups are, but maybe, or Siemens campus, I don't know, it's there, people there will work with Python. Of course, the benefit of Python is that it's free, and MATLAB is not free, but you have to pay for licenses. And so over the last years, there's been, I wouldn't say there hasn't been like real tension, but it's kind of that. On the one hand, if you join labs here, they might still use a lot of MATLAB, but then we also have people in the courses the young people who rather in their previous experience have learned some Python, and I think also Python is kind of more sustainable and it's more sensible to teach Python. So Python will be programming in the summertime. Although it's in the summertime, I really recommend every one of you who's now studying cognitive neuroscience and wants to be a cognitive neuroscientist to essentially, if you haven't started to learn how to program, start today. And if you already have started learning how to program, learn more. Because it just takes some time, and also the summer course, like this lectures that we're doing here, is not that in these kind of 14 times 2 hours sessions you will become anywhere near at like writing your own programs. But again, these sessions in the summer term will help you to consolidate your knowledge, to apply your knowledge in programming, and maybe to gather new knowledge in programming. But in the end, to become self-efficient and proficient in programming, you just have to do it, and you have to do it yourself. So you cannot just by somebody telling you how programming works, you will never really learn how to program. So please get started on teaching yourself how to program now. And there are millions of introductory courses, notes, YouTube lectures, whatever on Python. And it really doesn't matter where you start. It might make sense to a little bit focus, if you're looking into Python stuff, to focus on numerical computing or something, and not necessarily app programming or website programming, because that's not what you mainly will do if you are a cognitive neuroscientist. Yeah, just do that. Of course, there will be some material also shared with the course once we are at the course. But there's really, I mean, there are so many books on Python. There's so much free material. So just do the Python tutorial, for example. So Python, the whole Python language comes with a big tutorial and a short version of the tutorial. So just do it. Just start doing it, please. Because otherwise, so the practical stuff that you do in cognitive neuroscience is essentially programming and acquiring data and writing papers. So and of course then talking about your research. But it's really a very important part of the of being a cognitive neuroscience data scientist. Yeah. So any questions about the programming right now? Python, we will do a little bit of MATLAB maybe, but mainly Python.
Like what level of expertise do you suggest we have for the course? Like how much of Python should we know?
It's really up to you. The higher the better. Okay. So just start today being a cognitive neuroscientist and make cognitive neuroscience better. Not great again, it was never great, make it better. And you can only do that by knowing your methods, meaning that you know roughly what EEG and fMRI is, knowing kind of the cognitive neuroscience literature, but then mainly knowing math, knowing data analysis, knowing statistics, knowing machine learning techniques, knowing artificial intelligence, and knowing programming. And all of this you should start today.
Should we focus on some specific toolboxes while we're learning, like NumPy or something?
Yeah, NumPy, like I said, so numerical mathematics, things like whatever you can do in numerical mathematics, but yeah, so there are also like books like data analysis with Python. You can also look into those. Yeah, so so definitely cognitive neuroscience is kind of applied mathematics in the sense that yeah, you need numerical computing, you need statistics, you can look into, so I mean, of course there are also many toolboxes that do things for you, and you can look how to use them. Yeah, just yeah. There will also be actually a programming course for the data science people. I'm not quite sure whether you're allowed to join them in the winter term, because that's what they have to decide, but it will happen on Wednesday, so I'm also not sure whether it will clash with your program, but they will do C++, I think, and Python. So wherever you can expose yourself to programming, do like 1 hour of programming every day from now on, and then things will be awesome.
When we do the programming, like, are there any recommendation, like, for the framework, the notebook, PyCharm, anything? Like, when we do the programming, like, are there any recommendation for the tool, like PyCharm or Jupyter Notebook?
You mean in terms of how you write code? Yeah, so I use Anaconda and the Spider interface, which is mainly due to the fact that I started most of my programming in MATLAB, and the Spider, I think it's called IDE, right? It's called IDE, is most closely, well, it's modeled kind of on MATLAB, on the MATLAB interface, so that's why I prefer it. Jupyter Notebooks, yeah, you can, I mean, it doesn't hurt. And actually, in the data science statistics course, I will also ask people to do their exercises in Jupyter Notebooks. I find for cognitive neuroscience, if you do a research project in cognitive neuroscience, usually you will not in the end up with a Jupyter Notebook, but you want to have all your scripts and running, and because you still have the paper separate from the code, which also makes sense in cognitive neuroscience. So Jupyter Notebooks are not kind of the standard way to communicate right now. So you can use them. They sometimes, I think, make things a little bit messy. So yeah, I use the Anaconda distribution and Spider. Any other questions? No? Good. Then course requirements. So what do we have to do to pass the course? So obviously you have to do something for new cognitive methods, and you will have to do something for programming. For programming, I am not quite clear yet what you will have to do. So I will look again what you did last year and what worked and what did not. But of course, what you will have to do for programming will also only be really be important in the summer term, which is still a couple of months to go, 8 or something, 3, no, 6, something, whatever. So there's still some time. But what do you have to do for neurocognitive methods? So for neurocognitive methods, you will have to pass an oral exam. And this oral exam will also be the basis of your mark for the neurocognitive methods and programming module. So essentially what you will do in programming will count towards your active participation, but will not be graded. What will be graded is your performance in the oral exam. The oral exam will take roughly 15 minutes. And you have to essentially take this oral exam until a year from now to complete, if you also complete the programming part, to complete the entire module in the academic year 1920. If you don't take the oral exam in this time, then so until September 30, 2020, then you have not passed the module in the 1920 academic year. The oral exam will be offered at multiple dates. So in the winter term, I offer it before Christmas, so that you basically have between now and Christmas to learn these things. And of course, I recommend this date, but you don't have to take this date. You can also then do it in mid-February, so after the exam. You can also do it at the beginning, essentially, or briefly before the beginning of the summer term. And in addition, you will be also able to do it at the end of the summer term and at the beginning of or roughly at the beginning of the winter term, so around the end of September next year. Yeah. So I recommend doing this exam here so that you actually, for all your other courses and also for your own sense of accomplishment, have this out of the way and have it before Christmas, so that you can, for example, focus on studying for the statistical methods exam, which one of them will also happen around this time, but more about this. You've seen that maybe, but we will talk about this later. You can focus on that later. Yeah, so as for the oral exams, there is no formal kind of thing that you have to declare that you're taking the exam then and there. I will set up, but this I will do in like December, early December. I will set up kind of I call it exam planner last year, where you can just like in a Google Doc write in when you want to take it, so that I roughly know who wants to take it. But then if you don't show up, then you just didn't take the exam and take it again, or take it then at another date. Yeah. And the exam, I will do the exam with somebody else sitting in, and that's essentially what I can say about the oral exam. I think you can fail it up to 3 times, but usually no one fails. And if it turns out that you're likely to fail, then I usually recommend that we forget that we just did an oral exam and do it at a later time point. You just need to pass it. It will be 3 questions on EEG and 3 questions on fMRI. The more you talk, the better. But I guess I will come back to that in December or so, closer to the date. Yeah, and the content, so what we will discuss in the exam is based on the slides that I present here. So although you hopefully read the book, in the books there's also stuff that is in addition to what I present here, and only what I present here will be you will be asked about in the exam. Good, and what you will have to do in terms of active participation in the summer term will still be decided, but of course it will come down to that you write some programs and maybe also document your programs and write a little text or something like this, how exactly this will then be later be decided. Yeah? Questions about this right now?
Are the things in the course that you presented art in the book?
Yes, but few. So, yeah. Anything else? No. Good. Then this was kind of the formal introduction to neurocognitive methods and programming. Of course, we will come back to it, and obviously I will see you every week on statistical methods. So if there are urgent questions also regarding neurocognitive methods, then we can also discuss them in statistical methods. Good. Then we now start for the remainder of this first hour with the introduction to EEG. Actually at 12, Miriam Bartra announced that she will visit us. So we have now until 12, and then Miriam will show up and introduce herself. So, and you have all the slides. Yeah, so essentially, and I don't think I will change much of the slides because they've been through a couple of iterations, and just if you, I don't know, you can put your own notes to the slides if you want. Obviously, so do whatever you want with the slides, but you should be all set. Good. First, introduction to EG, and the common slide to start these things is actually a picture from the Hüttel book, from the FMI book, which shows kind of the tool set of, I think I will sit down now, because then you also have the online pointer. The tool set of cognitive neuroscience, basically allocating every imaging technique or every data acquisition technique somewhere in a spatial domain of resolution and a temporal domain of resolution, and also relating it to neural structures that you will have heard of. So, of course, I assume that you have all seen this before, and of course, with choosing to study cognitive neuroscience, in a way, you also made a decision of where in this kind of spatio-temporal resolution space you want to work, because cognitive neuroscience is not done with patch clamp recording, usually. So does anyone know what patch clamp recording is? You can briefly explain that to us. It's usually the biologists who know that. But do we have a biologist?
Oh, I'm not a biologist.
No, but you know what it is.
Yeah, it's when you measure, for example, ion channels and you measure the action, the potential. You have like a very small waves, small particles. And you put it on an ion channel and then you measure the current.
Exactly. So, so usually you do that in some kind of cell preparation and so on. And this is then usually in vitro. You basically just have part of the animal there, so there's not too much cognition going on. It's a different field, so I also have to say, so if you go to for example, if you see computational cognitive neuroscience as being part of cognitive neuroscience, I think there wasn't any patch clamp recording on this. Doesn't mean that it's not possible, but you have to be kind of very inventive to research on cognitive processes using patch clamp recordings. Where actually more kind of cognitive neuroscience is happening these days is in animal optical techniques, because they have come quite far, I think, or at least I believe, or something, over the last 10 years, so that it seems, although I'm really not an expert on all of this animal optical imaging, that you can more and more also have behaving animals, so especially mice, where you do some optical imaging, and these mice behave and they do something in some kind of maze or something, which goes in the direction of cognitive neuroscience, definitely. But then, of course, is kind of the cognitive neuroscience of mice. Single unit recordings, where you essentially poke electrodes into brains, of course, still happen. I think, or my feeling is that like 15 years or so when I started in neuroscience, there was more monkey work around than I see these days because of ethics. Of course, it gets much more complicated. And the question is also whether we as cognitive neuroscientists actually want this. So I think monkey physiology is a little bit on the decline, maybe being replaced by rodent physiology, something like this. So I think, thinking about it, I remember one master thesis that actually worked not in invasive recordings, but at least worked on a cellular level. So it's a rare case for people in SCAN to, in the end, start working with these kind of techniques. But it happens, and if you really feel like, oh, this non-invasive brain imaging, that's not the real neuro, then yeah, you can also, I mean, there are labs in Berlin that use these techniques, and you can also join them. My personal opinion is that whatever you use to record something, what you record in the end is a signal in your recording device, and you need to make sense of that. And you have to do this the same way using a patch clamp recording, where you then have the theory that there are things like ion channels that are gated in certain ways, or you have it in your electrode, where you then filter out certain things and call certain things spikes. So you have to make some sense. And the same thing with the techniques that we are mainly using. Talking about single unit recordings, of course, you can also, some patients with deep brain stimulation, for example, or epilepsy, they also have electrodes essentially in their brains for medical reasons. And there's also, there are also experiments with these kind of patients that are also done in Berlin at Charité, for example, Wales. And so these single unit or intracranial recordings also happen with humans. However, this would be then usually close to a clinical setting. So in what we here use at psychology is, of course, EEG. Looking, for example, at ERPs. Sorry, this is actually the MEG box. The EEG box, I think, is here. We use EEG and fMRI. We also have a TMS machine. So does anyone know what TMS is?
Transcranial magnetic stimulation.
And what is it used for?
It induces activity in the brain and these electrical magnetic minor shocks that are usually harmless, or it inhibits the activity.
Yeah, exactly. So it basically intervenes with ongoing activity and can be used in different ways. To excite something, but also to inhibit things. There's also, which is I think not on this slide, these direct current stimulations, where you essentially just put an electrode somewhere and on the scalp, and instead of recording what's going on, you have some electrical activity being applied. This became more popular, is my feeling, over the last 5 years. So I see that more and more. We also have that in the seminar series sometimes. I mean, I don't see it really more and more, but I see it occasionally. It seems even more unspecific than TMS in terms of what it really does, but there's research on that, and we also have machines actually to do that. What we don't have is an MEG, which records the magnetic fields of the brain and is by and large very similar to EEG. If you really go into details there, then it's basically may have a little bit of better spatial resolution, but that's not really clear. It definitely doesn't image deep sources, and it focuses on tangential activity, and EEG captures a little bit more. Thing is, MEG is of course also quite expensive because it needs a lot of cooling. But there have also been some developments, and I will briefly talk about EEG and MEG, kind of a modern take on that in a second. What else do we have? PET. Does anyone remember what PET is? Tomography, what? And do you remember how that works? you need some radioactive tracer. It used to be the thing in the 80s that people used before the advent of fMRI. So, for example, you attach some radioactive material to glucose molecules, and then you inject that into the veins of your participant, and then the idea is that if brain area is active, they need to uptake glucose, and then these radioactive particles decayed and emit positrons, hence the positron emission, and this was then detected in a ring detector. It is still being used mainly for kind of receptor mapping and so on, but because it involves radioactivity and is invasive in terms of injecting tracers, it's something that again you will find more in a clinical setting, definitely not here. Drug manipulations, if you go to more long-range effects, drug manipulations, you also find here. So for example, Hauke here does some work on stress and decision making and the neuropharmacology of that. So that also happens, of course, then usually together with some medical faculty. And lesion studies are also, so in terms of neuropsychology, they definitely exist. I think Hans Otto Karnert in Germany is still the neuropsychology guy. We don't have a neuropsychology group here. So neuropsychology meaning that you study people with a stroke or other lesions of the brain, but still happens. So that's kind of the big the big set of methods that you can potentially use. The thing is, in a way, all these different methods come with their own fields. Yeah? So, for example, if you are interested in drug manipulations, you will basically go to neuropharmacology conferences and will be kind of in the neuropharmacology scene. Or if you're doing neuropsychology, you would more be talking to people who do neuropsychology. Same for patch clamp and single unit recording. So the scene that you find here at FU and that this program is really related to is the scene of people that use EEG, fMRI, MEG, and of course, which is not here at all, behavioral methods, meaning that we record the behavior of participants as they respond to stimuli or something else. Yeah. So kind of EEG, fMRI, MEG, these are the dominant things that you will find at, for example, things like human brain mapping, the OHBM big society, or of course where I'm situated at computational cognitive neuroscience, we saw EEG, MEG. There was a little bit of invasive stuff, right? There was a little bit of monkey stuff also. Seem to remember, but maybe also not.
What about DTI?
Genetics, maybe, I think.
What was this? Genetics, animal optical techniques. Yeah, DTI. Yeah. So when it says here fMRI, I always think of MRI. So DTI, diffusion tensor imaging, to trace. Or the way it's mainly applied to trace the connectivity, the anatomical connectivity in the brain. I would consider that part of the MRI thing, but I would not consider that part actually of. So if I'm really kind of picky, I would not necessarily consider DTI to be part, or that it should be part of cognitive neuroscience, or let's say, so the thing is, it doesn't do function very well, right? So with fMRI and ERPs, you are interested in ongoing cognitive processes that relate, and their ongoing neural activity, and DTI as a structural thing would not really be doing functional or neurocognitive imaging. However, that's just me being very picky. Of course, in cognitive neuroimaging, there's a lot of DTI And there's also a lot. There used to be. It's very hard to tell sometimes because there used to be quite a lot of structural imaging. Then structural imaging, so looking just at the anatomy, was away for a couple of years. Didn't see anything anymore, and I thought nothing happens anymore with structural imaging. Not that I was particularly interested in. But then again, you have a spike of structural imaging. It's a little bit hard to predict. But yeah, so DTI and anatomical imaging, being in the MRI thing.
Do we have a chance to use necessary equipment for DTI in our research institutes?
Sure. So with an MR scanner, you can use all sorts of sequences, and DTI is just a specific sequence that we also have. And for some reason, the most cited paper that I have is on correlating DTI connectivity with functional connectivity. It's one of the most boring papers ever, but people love resting state and hence default networks. It's really big, resting state. So one of the reasons why I stopped going to OHBM, so the Human Brain Mapping Conference, is because it was just resting state. And resting state is fine, but and it's also interesting. But of course, if you're interested in how in models and theories about cognitive processes, then you have to do a little bit more than just record another resting state data set and measure functional connectivity, because then, of course, what is interesting is how resting state fluctuations interact with cognitive processes. That's very interesting. That always has been interesting. But a lot, from my perspective, on resting state stuff has been essentially just recording resting state, doing voxel-by-voxel correlations, and then applying graph theory, and then what? So where the link to cognition got a little bit lost. Of course, you don't. This is just speaking strictly from a neurocognitive perspective, because of course there are also relevant resting state studies or default mode network studies relating, for example, to clinical symptoms. So it might be interesting to figure out whether one can use resting state scans as a biomarker for early onset schizophrenia, depression, or something like that. That's all very interesting. It's just not clarifying the neural basis of cognition in my interpretation. Good. Any other questions right now about these general methods that we have here? Something that you never heard of or on the slide, or something that you always wanted to know about but were afraid to ask?
Like about TMS, would you say that's actually harmless? Because like that does sound pretty bad to me, like to put large magnetic fields into your brain.
Yeah, it's harmless. I don't use it. I also don't like it. So I was in Tübingen. I was a participant in TMS studies, and what I didn't like was that you have this peripheral stimulation. So in addition to your brain being stimulated and maybe your limbs twitching, which was the idea, you also have the peripheral nerves in your skin being stimulated, and it zaps, and it's just a little bit, it's not really painful, but it's not nice. So it's like touching an electrical fence, for example. I don't think there have been any studies or making waves that TMS is really, so the way it's being used in cognitive neuroscience, is harmful in any way. Same goes for MRI. I think there has never been a big claim that MRI, after now almost 40 years or so of MRI, after we said for 40 years that it's not harmful, is suddenly harmful. So I don't think that this is the case. I also don't think that TMS is harmful. However, it induces temporary lesions, and I personally, I don't want to use it. I find it very unspecific and also not causal, in the sense that it's often sold as that this is causal, because in the end you correlate your TMS protocol with your behavioral stuff. So it's as causal as anything. So personally, it's not my favorite tool, but I don't think it's harmful. Or I don't know of any studies that claim that it's harmful and we should all stop doing it. Good. Then we can actually stop here. Actually, Miriam, is she here? No. Should be here any minute. So we take a break until 1/4 or maybe 20 past, depending on how this thing with Miriam goes. Yeah? Good.